So there will be a short question break in the middle of the presentation. Um, okay, I'm sorry. There we go. Apologies. I'm jumping over to the side there. There will be a short break for questions in the middle of the presentation. So feel free to hang on to your questions till then. If you want to, you'll get a chance to unmute yourself and ask Amy verbally. You may also put questions in the chat. And then we'll have a Q&A session at the end as well. So you have a couple ways. Amy's email address is also in the chat, so you may always email her later on. If we have time in either of those Q&A sessions, I may grab some of the questions from the chat to ask out loud, and then she can answer those verbally. So we'll just do whatever we can with those today. So I think I can actually focus now. My name is Aidan Barnes. I am the Director of Programs and Partnerships with the C&O Canal Trust. We are the official nonprofit partner of the C&O Canal National Historical Park. A little bit about the trust work. We support the park through fundraising and programming, such as volunteer programs and community activities and preservation and restoration initiatives. One such initiative that we have is our Canal Quarters program, which focuses on 7 1830s era lock houses throughout the park, which we have rehabilitated for modern overnight guests such as yourselves. You may spend a night in an 1830s era historical house in the C&O Canal. That is on our website, canaltrust.org. You can read all about that, and I can drop a link to that one as well. And rare, threatened, and endangered plant species as well, raising funds and supporting the park's initiatives to protect those too. Okay, so Amy, if you want to jump to the next slide. Okay, there we go. So let's start with a little bit of park history. We may have some folks here who maybe are not in the area or not familiar with the C&O Canal. You can see on this map, she's drawn it in blue. That is the Potomac River in the blue, and that's also the C&O Canal. It runs from Georgetown in Washington, D.C. out to Cumberland, Maryland in the Appalachian Mountains. She's got a couple other cities marked there. Park headquarters are just west of Hagerstown, Maryland, in the middle, right there. It runs for 184 and a half miles. That's the distance from Georgetown to Cumberland, at least as the canal flows. The main artery through the park, other than the canal itself, is the towpath, which today is a multi-use recreational trail that is popular for runners, cyclists, walkers, backpackers, horseback riders, birders, and many more. You can see the towpath featured in both the modern and historic photos on this slide right here. The C&O Canal was originally the brainchild of George Washington in the late 18th century. He dreamed of an inland water trade route to connect the eastern seaboard, Chesapeake Bay, with the Ohio River, Pittsburgh, which is where we get the name of the canal, Chesapeake and Ohio, or C&O for short. On July 4th, 1828, the canal companies broke ground for the canal right around Little Falls, just outside of Washington, D.C. Its purpose was to ferry coal, lumber, agricultural, and other products from the Appalachian Mountains to the trade centers at either end. And at either end is the Ohio River, just outside of Pittsburgh. It's not Cumberland. That's where they were going for. And the canal boats, laden with as much as 120 tons of coal, were pulled by mules who walked on the towpath beside the canal. In the building of the canal and then the operating of it, the canal companies and the engineers and all of the workers faced many, many, many hardships and challenges the entire time, including endless rocks, yes, rocks, and mountains to dig through, more on rocks later, Floods, labor disputes, higher than anticipated costs, and the ever-increasing competition with the railroad. That is the Baltimore and Ohio, the B&O Railroad, which ironically also broke ground on the exact same day, July 4th, 1828, in Baltimore. One second, I'm sorry. Um, okay, that's fine. Um, in 1850, they stopped building in Cumberland. That's just as far as they got. They ran out of money, and too many of those challenges were too difficult to overcome. The canal remained the 184 and a half miles that it is today. In 1924, after a series of devastating floods, the canal ceased operating. It sat unused until the National Park Service acquired it in 1938, though many people did live and recreate and work their own businesses there on the land and the water. And in 1971, it became the C&O Canal National Historical Park. But let's go back to those rocks that we promised to talk about, and way before the year 1828 and even George Washington, which is actually why we're here today. So I'm going to turn it over to Amy and let her take it away. Amy.
Great. Thanks, Aiden, and thanks for organizing this.
Sorry, Amy. I meant to mute myself. I muted you.
Okay, no problem.
Apologies. Start over.
Okay, yes. Hello, everyone. Thanks for coming tonight. I'm really excited to tell you about my experience working doing geology research at the C&O Canal, tell you a bit about the area. But first, I want to introduce myself. My name is Amy. I am actually from Maryland. I was born, or not born, raised in Calvert County. I then got a geoscience degree from a small liberal arts college in Massachusetts. And I got into geology research while I was there. And so I decided to pursue a PhD at Virginia Tech, which is where I am right now. It's my fourth year, so I'm actually almost done. And a lot of my dissertation work has been at the C&O Canal. Some of the things I'm really interested in, I use the chemistry of rocks to study the oceans. So I use sedimentary rocks that were deposited in the oceans to figure out what different chemical parameters of the oceans were millions of years ago. I like to focus on animal extinction events and try and figure out what caused them. And I also love the Paleozoic era, which don't worry, we're going to talk about all this, which was when animals were first rapidly evolving and diversifying. So that's just a taste of who I am, give you some background on my perspective. So I know we're not all geologists, so I wanted to start with a quick few slides of review. So some of us might remember from learning in high school, perhaps, the three different types of rocks. So to begin, we have igneous rocks, which are usually formed by volcanoes or magma under the surface. They usually have big crystals of different minerals. And they can tell people who study them things about volcanic processes and temperatures within the earth. We also have sedimentary rocks, which are my favorite. And these are ones that have formed in the ocean, usually from the erosion of rocks coming from the land. I put an asterisk here because if you're a geologist, you might realize that this is a limestone, which is actually a particular type of sedimentary rock that actually precipitates out of the ocean. So the bit about erosion from land is not quite true for this particular rock, but is pretty true in general for sedimentary rocks. And then finally, we have metamorphic rocks. These can be any type of rock that has been squished or squeezed by tectonic processes, by plates moving around, by volcanoes in the area altering other rocks. I also wanted to talk briefly about the history of the Earth, which will be really important for some things I'm going to talk about later. I really like this art from a paleo artist that shows sort of the timeline of Earth history in relation to life and evolution. So the first thing that is really important is that the Earth is about 4.6 billion years old. So it's really quite old. And life evolved about 3.7 billion years ago, and these were microbes. And they lasted for quite a long time until we had the first animals evolving about 540 million years ago during this period called the Cambrian, which I'm going to mention a lot tonight. Um, and so the Cambrian, you may have heard of the Cambrian explosion as a term. We sort of had no large animals, and then all of a sudden we had a lot of animals, different groups. Every group of animals today that you might see outside, the roots of those animals were established in the Cambrian period. So this is a really important time for evolution. There were also 5 mass extinctions in Earth's history. You might have heard of one of them, the asteroid that killed the dinosaurs about 65 million years ago. But there were 4 others. These are all times when a large percentage of the different groups of animals went extinct all at once. And that caused a lot of stress to ecosystems and ended up with the assortment of animals that we have today. So understanding the history of the Earth is really important for figuring out what's going on with the species and the arrangement that we see today. I also wanted to briefly mention the concept of plate tectonics. So this is the idea that the arrangement of all the continents is constantly in flux. They sit on different tectonic plates and they move around over time. And this is actually a pretty new idea. This wasn't really accepted in geology until like the 1960s. So for a lot of science history, we did not know about this. So one thing that this means is that the climate on continents that we have today may have been very different in the past. So just as a fun example, Antarctica, which is now, a very polar, snowy place, used to be tropical. It used to have tropical rainforests and fossils that we can study today and learn about what that climate used to be like. Another important concept about plate tectonics is that when these plates collide with each other, we can build mountains. So that will be important when we talk about the formation of the Appalachian Mountains later. So coming back to Maryland, which is what we're all here for, Maryland can be divided into 3 different sort of regions. So I've drawn the lines here. We have the coastal plain, which is where Calvert County is, where I grew up, and sort of the area directly surrounding the Chesapeake Bay. This is all made up of loose sands and gravels from the last 2.6 million years. So this part of Maryland used to be submerged pretty recently. And so all that sand, like you might find in the ocean today, is what makes up the land surrounding the bay. And this results in a really flat landscape. We don't have a lot of mountains in this part of Maryland. And then the second region is called the Piedmont. This is made up of metamorphic and igneous rocks, and they can be quite old, about 1 billion years ago to 200 million years ago. So this is a slightly older time when at different points throughout its history, there was volcanism or there were collisions that really altered these rocks and made them into metamorphic rocks. So we don't see any of the sedimentary rocks that we see in the coastal plain anymore. And this landscape is not flat anymore. We now have sort of a gently rolling landscape with isolated mountainous areas in this region of Maryland. And then finally, we have the Appalachians, which is what I will be talking about today. These are made up of folded and faulted sedimentary rocks. They are of Paleozoic age, which I mentioned was my favorite. And this is about 540 to 252 million years ago. So these are sort of limestones, sandstones, shales, rocks like that have been folded up over each other and faulted against each other during the formation of the mountains. So this part of Maryland is really mountainous. The highest peak in Maryland is sort of in the westernmost little triangle over in the corner over here. So how did we end up with these 3 different regions? Why do we have these rocks in these places? And then why are the rocks at C&O Canal so special to me, and why should they be special to you? So I'm going to talk a bit about the formation of the Appalachians. I've made my own time scale on the right here. So we've got sort of the what we call the Precambrian, which was when we didn't have animals. Then we've got the Paleozoic. Let me just move my zoom bar here. Okay. Paleozoic, we started getting animal diversification. We started out with invertebrates. Slowly, we ended up with fish and other vertebrates. Then we have the Mesozoic, which is well known for its dinosaurs. And finally, we have the Cenozoic, which had humans and the ice ages, large animals like that. So now I'm going to step you through the formation of the Appalachians relative to this time scale. So the oldest rocks that you can find in the Appalachians were formed when some continents collided about 1 billion years ago, and it's called the Grenville orogeny. So you may have heard of Pangaea in the past as a supercontinent. Well, Pangaea was not the first supercontinent. So before Pangaea, we had the supercontinent called Rodinia, which is shown here. So it's pretty much most of the continents that we know of today, all crammed together sort of around the South Pole. So this was about 1 billion years ago, so before any animals were around. And the fact that these rocks are so old means that the rocks are highly metamorphosed now. So we don't have any sedimentary rocks anymore. We just have metamorphic rocks like gneisses or schists. I won't be emphasizing them too much today because I am a sedimentologist and I care about sedimentary rocks. Okay, so a bit later in the Paleozoic, we had the formation of the Appalachian Mountains. And so when we learn about this in geology class, we learn about these three different collisions. The ultimate product of these collisions was Pangaea, so that's pretty exciting. And they have three different names, the Taconic, Akkadian, and Alleghenian. And you might recognize, the Alleghenies are a mountain range, so we sort of share names in that regard. But this map here sort of shows what North America would have looked like. They've even overlaid some of the state boundaries here, but actually a lot of North America was underwater a bit. And then we had these islands forming off the coast here that would repeatedly smash into the East Coast. So it's these sort of processes that built up the Appalachians over at least three different collisions. And so these rocks that form the Appalachians are about 460 to 300 million years old, and they're mostly sedimentary rocks. And so this diagram sort of shows, we've got North America over here, which we call it Laurentia. It's the name of the continent before it became North America. And we've got these islands forming out here. And in between the islands, we've got this really shallow sea. And so sedimentary rocks were forming in those seas. And then as the islands smashed against North America, those sedimentary rocks became attached. And so this is really great for me to study because we had sort of constant sedimentary rock formation throughout this whole time. And they are now preserved, all grouped together over in the Appalachian Mountains. So since the formation of the Appalachians, since about the Paleozoic, the Appalachians have just been weathering. Some fun facts that people like to say about the Appalachians is that they used to be as tall as the Himalaya, which I think is true. They're just older, and so they've had a lot more time to weather away. So the breakup of Pangaea, which I've included a picture, a representation of here, meant that we didn't have any more collisions. We were no longer building up the Appalachians, and so they just have been weathering since. For your reference here would be North America, and then Maryland would probably sit where this pink star is. And then about 2 million years ago, during the last of the ice ages, the Potomac River formed. So the Potomac River runs the border between Maryland and Virginia and West Virginia. And so this is a photo of it at Great Falls, which is another visitor center at the C&O Canal. And so the river cut through these old sedimentary rocks, which nicely exposed them for us to study today. All right, so that was a bit of information, maybe a lot for some of us that may not have had a lot of geology in school. And so I wanted to give an opportunity now, if people have any questions about any of that, to go ahead and ask.
Feel free to unmute yourself if you want to. Okay, we have a question in the chat. What is your dissertation subject?
Oh, um, there's a lot of subjects. I'm actually, if that's okay, going to delay that to the end because I'm going to talk a little bit about some things that are in my dissertation. And then I'll make sure to fully address that at the last question break, if that's okay.
Great, thanks for asking that, Dan. Are you going to talk about the opening of the oceans back and forth?
Yeah, so I think I kind of touched on that a bit when we were talking about sort of these processes here. I've only touched on the oceans that are relevant to Maryland, but this sort of movement of plates opening and closing happened many times since the formation of the Earth. It sort of happens in cycles. Every 500 million years, we have a supercontinent form, and then diverge. And then even when we don't have that happening, we have sea level changes. These can be driven by glaciers or climate warming. Things like that can affect the sea level. And I'm actually going to talk a little bit more about that when I talk about some of the rocks that we can see at C&O Canal. So hopefully that answered your question.
So we have maybe 200 to 300 million more years before this happens again?
Yeah, they've actually already named the future supercontinent as Pangea Ultima, and they've already modeled, what it'll look like. So none of us will be around to see, but people are thinking about that.
It's amazing. Okay. Well, maybe we can continue on and catch more questions a little later.
All right. Cool. Okay, so we talked a bit about the sort of regional context of the C&O Canal, and now I'm going to tell you a bit about things that I have observed in the rocks during my work there. So first, a disclaimer that I'm not going to talk about the entire length of the C&O Canal. The areas where I have worked are actually only about 2 miles worth of the canal, and they are located sort of near west of Hagerstown, near the town of Clear Spring, Maryland. The Four Locks boat ramp is sort of over here, and then the town of Williamsport is over here, and my study areas go along the towpath in these two different spots. And so these spots are very specific sedimentary rocks from the Cambrian and Ordovician periods, which are the periods that I'm interested in studying and my colleagues are as well. And so during this Cambrian period, North America was actually turned sideways and at the equator. So if you can imagine this continent of Laurentia, which is actually North America, is sort of taken, turned sideways. So Maryland would be sort of over here on the south side. And it was at the equator. So this means that it was very tropical. So if you imagine going to the Bahamas today, that would sort of be what it would be like in Maryland 500 million years ago. So uh, the tropical environment would have formed these white sands made out of calcium carbonate. So this includes minerals like calcite and dolomite, if you're familiar with those. Basically, these are minerals that precipitate directly out of seawater under really tropical conditions where we have a lot of calcium in the water. And so now for my favorite part, I'm going to show you some of the best features that we have noticed when working at the C&O Canal in the limestones. So the first, these are called ooids, and these are very strange. I had never heard of them until I started doing research in college. But these are small spherical balls of this calcium carbonate. Um, and they actually form by rolling around on the seafloor, kind of like a snowball. So if you imagine you rolling it, it builds up layers on the outside, and you end up with this sort of jawbreaker like sphere. And so this is what they look like when we're out in the field. We can hammer off some of the rock and see these little round balls making up the rock. This is a sample of ooids from the modern. So even if you've never heard of them or seen them, they do occur in a few places today. They definitely occur in the Bahamas and in other tropical environments like that. We also get them forming in the Great Salt Lake in Utah. So if you're ever out there, go ahead and take a look at the sand. And then we can also look at them under the microscope. So this is a technique where we take a rock, like this piece right here, we would glue it to a glass slide and shave it down really thin, and then we can see through the rock. And so this helps us look at all the tiny features we might not be able to see when we're actually out there. We can take them back to the lab and get a better look. So these are what ooids look like zoomed in under the microscope. So you can kind of see they have these centers, and then they would have had material built up as they rolled around on the seafloor. So I think these are really cool. I get really excited when we see them in the field. They mean that they're kind of like sand in a modern environment. There's lots of waves going on. They're rolling around. It's very tropical and warm. We also find ripples at the C&O Canal. So this might be something that you've seen when you've been to the beach. So these are marks that form when waves are moving sand back and forth. When we see these in rocks, it means that the water used to be really shallow, right? You don't really tend to get ripples if your water's super deep. You need waves to be moving it. Um, and so this is one of my favorite photos from working at the C&O Canal, this really awesome rock face with these ripples all sort of going in a parallel direction. And so one thing we can do with the ripples is we can tell which way the water was flowing. So in this case, the water would have been flowing either up or down this face. So ripples are very fun. You might be able to see this if you were to walk along the cliffs near Four Locks. We also do find mud cracks pretty often. So you may have, after some rain or some hot weather after rain, have seen sort of mud with these deep cracks. You find this a lot out in the desert. You can find it at the beach as well. But we are able to see that in rocks sometimes. So if you look at this photo here, you can sort of trace these little cracks through the rock here. So basically, that sediment had dried up, and then new sediment has come and filling in those cracks. So now we are able to see them. So this, when I see this in the field, I know that this means that the water was really shallow and that it dried up pretty often. So usually that means that the climate was really hot, and also that the water may have been pretty salty. So this is good information for me as a geochemist. I also want to mention stromatolites. So these are another thing that I had never really heard of before doing research, but these are structures formed by cyanobacteria. So cyanobacteria live in the ocean and they photosynthesize, and they're usually quite sticky and they're microscopic. And so when they live, they sort of live on the surface of the seafloor, And because they're so sticky, they trap sediment. It gets stuck to them, and this can build up into mounds over time. So here is an example of a stromatolite today. We only have maybe 2 or 3 places in the world where you can find modern living stromatolites. One of them is in Australia. So this is a photo from Western Australia, and you can see these mounds have sort of grown up out of the water, and these are made up of bacteria growing for probably a really long time. And then when we look at the rocks at C&O Canal, we can see these sort of moundy structures. They have really fine sort of sheets of laminations. That's sort of one way that you can tell that cyanobacteria built these structures. Here's another photo where the mounds are quite small and they sort of grow vertically. There are other ones next door to them. So we see a lot of this at the C&O Canal. And there's also a microscopic view where you can see how thin these laminations really are. So each of those laminations would have been a layer of these cyanobacteria plus the sediment that got stuck to them. And then a new layer grows on top. And so when I see these structures in the rocks, I know that this was perhaps slightly deeper water than the other things we've talked about so far, because these cyanobacteria need it to be a bit calmer in order to grow into these big mounds. And then the last structure I want to talk about today are rip-up clasts. So this is kind of an unintuitive feature that we actually don't see very much in the modern. It's kind of hard to capture. So this is when we have pieces of rocks that have been ripped up into pieces during storms. So it was sort of a deep environment, rocks were forming, and then a storm would come by and rip them up and make a new rock. So in the field, you can see all these different chunks of other rocks that are now making up this bigger rock. And then under the microscope, we have this pebble made up of those ooids I was talking about, and it is now deposited into a new rock. So this is really interesting for us to see. We know that the climate had lots of storms. So now that we've seen all those structures, I hope I've convinced you that the limestones at C&O Canal are actually really interesting. They've got a lot of different structures. You might be able to see some if you hike along the cliffs in this area, and that these structures are really useful for knowing what the environment was like back in time, millions of years ago. So one of the things, the goals of me going to C&O Canal was to study evolution and extinction. So I wanted to include, this is a very famous graph of diversity of animals through time. So on this axis, we have the diversity of animals and the number of families, just a metric for diversity. And then we have time going from the Cambrian all the way to the present. And so this line sort of tracks the evolution and extinction of animals. And so if we look at the Cambrian, we can see that there's rapid evolution happening, but there's also these extinctions where the line sort of goes down briefly. And so I am really interested in what's causing those extinctions and these trends. And so I wanted to know if we could see these trends in the rocks at C&O Canal. And so I've compiled a bunch of images of the different fossils that we find. Most of them are microscopic, but you might be able to see some if you look at the rocks along the cliffs. And early on in the Cambrian, we see lots of different animals. So we see these animals called trilobites, which were used to be very abundant. They're related to animals like crabs or isopods, sort of bugs and insects. And they leave these fragments from their carapace, their skeleton. And so they make really good fossils, and we find them quite often. They usually make these sort of skinny, hook-shaped fossils. We also see brachiopods, which are sort of related to your normal sort of classic seashells like scallops that you might find on the beach today. However, they're actually completely different group. They have a different internal structure, but they sort of look like seashells. So we find some of those today. This sort of looks like, two halves of a shell. And then we also have echinoderms, which are just a name for the group that has things like sea urchins. And so they have this very porous skeleton. So when we find chunks like this, we know that they came from echinoderms. So early Cambrian stuff has a lot of fossils in it, and they're really cool groups. But as time goes on, we sort of stop seeing the fossils. And so we know from studying this time that there was an extinction event that happened here. So it sort of makes sense that we're no longer seeing fossils, even though the rocks are sort of similar, we're just missing the fossils. And then as time goes on, we start seeing the fossils again. But we only see trilobites for quite a long time. And so when I am looking at this for my dissertation, I'm trying to see how long did it take for the ecosystem to recover, and are there chemical reasons why it took so long? So here in these images, we have, again, these trilobite pieces that have this hook shape. Same with over here, but there's not a lot of other fossils in this time at all. So hopefully I've shown you that we have really cool fossils in the rocks at C&O Canal, and they tell a really cool story about early animal evolution. A lot of the fossils are microscopic, but if you're walking along the cliffs, keep your eyes peeled because you might be able to see some. And I wanted to highlight that it's really unusual to get rocks that cover this time period so consistently, and that the C&O Canal rocks are really special, and they're a really important resource for people like me that want to study the history of early animal evolution. So I wanted to briefly touch on some of the research that my team has been doing at C&O Canal. I'll just throw these topics out there and then feel free to ask me to elaborate on any of them. This is the group I brought up there most recently in the spring of this year. My advisor and some undergraduates and some of my graduate student colleagues, we were out there sampling. And my team has some people from Smith College, where I went to undergrad, and a colleague from Yale. And so we're interested in studying the carbon cycle on Earth. So that's one thing that I am really interested in. And so I use carbon isotopes, which may sound scary, but it's actually not too bad, to see if we can compile a record of the carbon cycle through time. We also study fossil abundance and diversity, which I touched on a bit with those images of fossils. We also, colleague at Yale studies animals burrowing into the seafloor, because believe it or not, we didn't always have that squishy layer at the seafloor where animals are burrowing. And so she wants to know when that started. And then myself and some undergraduates are working on these trilobite extinctions that we have recorded in the rocks and seeing if we can figure out what directly caused those. So I didn't have time to go into a deep dive on all these things, but feel free to ask questions about those. Um, and then as I wrap up here, I want to acknowledge that I could not do all this work by myself. It started 4 years ago when I was an undergraduate looking for a project to do during COVID. And so my advisor then at Smith College, Sarah, she was really instrumental in getting us the permits to work here at C&O Canal. My current advisor, Ben, and then a guy at the Maryland Geological Survey has been really helpful as well. And then I've also had an absolute team of people helping me sample these rocks over many years. And then I'm really grateful for the Park Service for allowing us to work in the park. And then I also want to invite you, I think we've got a good amount of time for questions, but if I don't get to yours or you have a more complicated question, don't hesitate to shoot me an email and I will get back to you. And then I also wanted to plug that we are doing a hike along the canal in December. So I'm coming up to Maryland and going to lead this hike on December 14th at 1 o'clock. We're going to leave from the Four Locks boat ramp and do a little hike, and I'll show you some of these features. Hopefully it'll be a lovely winter day. I'll talk you through we'll walk through time from the Cambrian to the Ordovician. I'll show you, talk about the animals that would have been evolving. I'll tell you sort of how we do this research, like how do I get these samples? What does it actually entail? And then I'm going to bring a bunch of rocks and maps and things. So if you want to come early and see those things, I'll be happy to show you. But we can't take everyone because I need to be able to talk to everyone and don't want to yell too loud. So the group size will be limited. So make sure you pre-register. And so you can go to canaltrust.org, and then the news and events tab has the hike listed. And so you can sign up there. So um yeah, I'm happy to take questions. I hope some of you maybe will make it out to the hike. But yeah, thanks for having me.
I also dropped the direct link into the chat.
Great.
So we got a couple of questions while you were talking. Which formation were you studying for ooids?
Mm. So the formations that I work with are called the Elbrook and the Conococheague, and both of those have lots of ooids. Um, they occur pretty often throughout the whole section. They're usually in these really big beds because sands are usually more resistant to erosion, so they occur in these big piles and they stick out really nicely. Um, but yeah, so if you wanted to look up more or read more about these, the Elbrook and the Conococheague are the ones that I've been studying so far, and there are ooids throughout both of those.
Cool. Are the ooids around because of their crystal edges got rubbed off, but the rock with the ripples was once horizontal, right?
Yes, I will go back to the ooids just for this question. Okay, yeah, so the ooids are so we are unsure if microbes played a role in the formation of ooids or not. So remember when I was talking about the stromatolites and the sticky cyanobacteria, we think that maybe cyanobacteria made ooids sticky, and so they'd roll around and pick up um, things as they rolled around. Um, Otherwise, the structure of the ooids is not, it's pretty amorphous. It doesn't have um, crystal edges, and they're pretty small. So it's not like we had something that got rubbed off. It's like we accumulated it in the round, if that makes sense. Sort of like you'd make a snowball, right? You're like taking a center, you're rolling it around to make the edges, as opposed to taking a block of snow and cutting off to make a snowball.
Mhm.
Hopefully that helps.
That's a good analogy. Yeah. Feel free to take yourself off mute if you want to and ask a question, or you can put it in the chat.
I have a question.
Yeah, go ahead.
This is a great talk, Amy. Thank you. I was wondering if there were any other places along the East Coast. I know you said that the fossil record on the C&O Canal was pretty continuous, but like if there are any other places that you have investigated to supplement that fossil record in any meaningful way that might be missing from the C&O Canal?
Yeah, great question. Yes. So although a lot of my dissertation is the C&O Canal, I've also been to many other places from the same time. So one project that I'm finishing up right now is using Maryland and also using two places in Virginia that cover the same time period to see if there are like differences between them. I mean, you'd think that if they're, as close as Maryland and Virginia are today, they should probably be pretty similar, but actually we see that there's some differences. So the sedimentation, the formation of these rocks in these different places is actually a bit different. Same with the animals, and that probably has to do with how deep the water was at each place. So if your water's super shallow or super deep, animals probably aren't going to want to live there as much as a place that is sort of in between. And then I've also looked at similar rocks from Utah and Newfoundland, Canada. And so uh, I don't usually do a lot of the fossil stuff, but my colleague at Smith College, she does a lot of fossil stuff. And so she's noticed that out in Utah, they have a lot of fossils all the time. But we see that extinction. And so we have questions like why extinction in Maryland and not in Utah? Again, I think it has to do with the water depth and that Maryland is a bit shallower than Utah was. So yeah, we definitely like to go to other places because one place on its own is not the same. Like around the world today, we have so many different environments. And so if we only studied one, we would be missing a lot. So that was a great question. Thanks for letting me talk about my other places.
Yeah.
Um, what gives the Canal Lock sandstone block their red color? The Seneca?
Hmm.
Mhm. I understand the quarry was near Seneca Creek. It's a little outside of your area, but do you know about that?
I can take an educated guess. Usually what makes rocks like yellow or orange or red would be iron. And we see that sometimes in our rocks as well, um, where there's some staining of things that are like red, rusty looking areas. And so that can be caused by the oxidation of iron that was in the rocks. I didn't talk about it a lot, but we have sandstones in these rocks as well. I focused only on the carbonate limestones in this talk, but we have sands, and we can get some staining of those just because sandstones are more likely to have little bits of iron that come in when they form, and those can become stained. I'm not familiar with that exact formation, but I would guess that it has something to do with iron, why they're colored.
A famous structure that's from the same quarry is the Smithsonian Castle,
Mm,
and the Washington, the mall.
mhm.
If you've ever seen that, or if you can picture that stone, that's the same Seneca sandstone.
Okay, yeah. I think we actually have an equivalent, if I'm right, down in Virginia, nearby where I live.
Mm.
Um, And so I think that's the fact that you're getting lots of erosion. You know, sandstones come from material from the land. And so if for some reason the material from the land already hasn't a color, you know, your sandstone will become that color. And so I think it's
Mm.
probably pieces of iron-rich rocks or other minerals like feldspars that are washing in, whereas, you know, our rocks are really pale because we're not getting a lot of that erosion.
Mhm. Yeah. And someone added Manassas red sandstone.
Hmm. Yeah, I'm definitely not a sandstone expert, but yeah, I would guess that those just have other components in them compared to these that are super pure carbonates, very white.
Hmm. Any other questions for Amy? Okay. Um, well, we did record this session, so the this wonderful presentation will be available, I hope pretty soon on our website. I think we'll stick it on the same link. So, um, thank you, Amy, very much for presenting to us today. It was very informative, and I didn't feel like I needed a degree in geology at all. So it was very accessible. Um, thank you very much, and thank you everyone for visiting. Um, you may still ask questions if you wish to, um, but thank you very much. We can end it here.
Thanks for coming, everyone.
Okay.